The speaker is Ronny Brendel. He's from TU Dresden, but he's out at Oak Ridge National Lab, helping them with their tools, Vampyre and Scorpy. And Ronny will be available on the Blue Jeans link after this talk during the hands-on session to help anybody who wants to try out Vampyre. And with that, I'll turn it over to you, Ronny.
Okay. Welcome again to my Scorpy Vampyre talk. For most of my professional life, I've been a Vampyre developer, and I worked on the predecessors of Scorpy and the underlying file formats. And now I'm at Oak Ridge, helping them basically use the tools. Sadly, I haven't seen the talks before, so I don't know how much introduction you already got. I just wanted to quickly reiterate that there is basically two overall methods to record performance information. One is the kind of called profile, where you basically accumulate data into buckets, which typically leads to small data sets. Static representation suffices. And the other kind is you basically do an exhaustive log of everything you see, so you can draw it over time. And this can possibly generate large overheads, and interactive presentation makes more sense in that case. Our tools are more located on the right side of this chart. There's two ways to intercept a program, two overarching ways. One is sampling, which most tools use. Instrumentation is also very common, but less common, I guess. Sampling intercepts a program in a given interval, mostly fixed intervals, and then probes the stack, asking where it is. And what you get by that is basically a statistical representation of what's going on in your program, because you probe at this interval, and you assume that, for example, the function you're hitting runs for the length of this interval. Instrumentation, on the other hand, gets a callback at every event, for example, a function enter and exit, and records exact timings. Yeah. And additionally, for example, has access to the arguments of the called functions, which can be beneficial, for example, when you want to know how many bytes are sent by an MPI send or CUDA malloc or something like that. Pedantically, it would look like this. You have an interception layer, which chooses between sampling and instrumentation. Then you have the choice to record it in a summarized way, or you log everything in detail. And depending on what you did before, you have the choice of displaying it as statistics or timelines. And loosely speaking, profiling and tracing are usually viewed in this space. I had a bunch of slides about misconceptions about tracing and profiling. I think I skipped these due to time. If someone tells you that tracing has giant overheads, that's technically not true, but a compiler instrumentation can be annoying, and filtering workflows are inconvenient. And they both have their ups and downs, and that's why most tools use a combination of them. For example, tools like Map or Scorpy, and probably HPC Toolkit and Tau as well, use a combination of sampling and instrumentation for getting MPI events and for recording message sizes, messaging partners, and stuff like that. That is the usual thing that's going on. So that was the quick method introduction, and now I come to the introduction of our tools. TU Dresden develops Vampyre and sells it through GWT, because German universities are not allowed to earn money. It has been developed for a long, long time. It is basically a trace visualizer. It is a program that visualizes an event log in many different ways and tries to give you insight into your program by presenting it in many different ways and very detailed ways. And it's interactive. And it also has a parallel backend where, if in case you have a giant recording, you can load it on an HPC supercomputer and still view it from your desktop leveraging lots of RAM, lots of compute power. Scopy, on the other hand, is our performance monitor, which has been developed more recently. It's basically a collaboration to unify performance recordings for the tools of our partners, because the tools are all kind of different, have different aims, but the recording infrastructure is very similar for all of us. So we began doing it together. Scopy itself is open source, and here is a rough architecture diagram of Scopy. I don't know how well you can read it. There is an interception layer, which leverages many kinds of interceptions. We hook into tools interfaces of CUDA, OpenACC, and MPI. We use source-to-source transformation for OpenMP at the moment, for example. Library wrappers, compiler instrumentations, many different ways to get into the program at certain points in time. And once you do that during runtime, there's many different things you can query. For example, the current time, the stack on which you are, the functions, hardware counters, information that is in /proc, or custom information via plugins. And from then on, there are two different file formats. One for the, I think I'm getting feedback, the detailed event trace, and the more coarse-grained profile. And those can be loaded by Vampyre on the one hand for traces, and Cube, for example, for profiles, and also Tau. Right, and there's lots of features to Scopy. We support many different HPC compilers, normal compilers, programming paradigms, all kinds of stuff. And I think one of the distinguishing things about Scopy and Vampyre is that you get one big picture about everything in your program. If you have a program that uses MPI, OpenMP, and OpenACC or CUDA, you still get a total picture of everything, and you can view your program like you programmed it, basically, and not like many of the vendor tools, very specific parts or lack of MPI integration or OpenMP. Scopy and Vampyre provide these things. All right, now onto the tutorial how to use them. So in order to load Scopy, you would usually module load Scopy. And on ORNL machines, I believe it's plus Vampyre to .soft and then resoft. And in order to compile something with Scopy, you just prefix your compile and link commands with the Scopy command, which basically intercepts this call and injects our measurement infrastructure into everything. That doesn't work for CMake and AutoTools workflows. That's why in this case it works a bit differently. You use a so-called wrapper script, and then you tell it via environment variables what to do. And during configure or CMake, you tell it to not do anything and just pass the call through to the compiler. And once you really do the make, you use it. It's necessary because configure commands try to compile and run examples. And on cross-compiling machines, for example, you cannot run things on the front-end node. That's why this is necessary. All right. Once you've compiled and linked your program, you just have to execute it with MPI run or shmem run or whatever. Then you have a measurement directory, which by default includes a profile. And then you can view this profile with Cube. Cube is part of Scopy, developed at Forschungszentrum Jülich. It lends its name through to its three columns. On the left, you have the available metrics like number of visits to a function or time spent in function or bytes sent and received. The middle has the call tree or the flat profile view, and the right side has the system view where you can You can, for example, click on a function in the profile and it will tell you the extent of the value on each of the MPI ranks or threads. So that was the profiling workflow. In order to trace, oh wait, yeah, there's a bunch of environment variables to customize your run. Those are some of the more important ones. Enable tracing, use performance counters. I don't know whether you heard of performance counters, but your CPU basically gives you a way to count cache misses, count floating point operations, and Scopy allows you to record these values on a per function call basis, so you have a very detailed view of what your function is up to. Right. In order to trace something with Vampyre, the workflow is slightly different. You add the environment variable Scopy enable tracing, and then you repeat the previous steps. Basically, you just run the example again. And this time around, the measurement directory will contain a few different files like traces.otf2. And this can be used to be opened with Vampyre. Yeah, on ORNL machines, you would have already loaded Vampyre. All right. Here's an overview picture of Vampyre. I will make a detailed demo of Vampyre in a second. Right. A warning about overhead. Trace size and overhead vary greatly between runs because function instrumentation is very unpredictable how many hooks you get into the program and how many calls someone does. So what you should always do is do a normal run and the profiling run, and then check the overhead and try to be below 10%. And maybe never be about 2x. And for that reason, we have a filtering workflow, which you should always follow when tracing. And I will explain it now. So recap, we just saw the profiling workflow, which is pretty simple. But this can also lead to problems because the default runtime filtering or the default execution still gets a hook for every function. And even if you don't do anything, 10 billion calls to a function can be too many. This is a problem. In the case for GCC, we have an instrumentation plugin, which allows us to be more clever about inlining with C++, for example, and usually yields way better results. And with our GCC instrumentation plugin, you can do compile time filtering. Yeah. The big problem is that when you have a C++ code and you use -f instrument function with GCC, you switch off inlining, which can kill performance because you unwind all the templates and see everything, which you don't want. That is why we have the compiler plugin. Okay, the tracing workflow is slightly different. You profile once, and then you use this profile to estimate how big a trace file would be. And from then you create a filter, and you use this filter for subsequent tracing. And you have a way to check how your filter is doing in terms of the estimation. Then you trace, and then you can analyze it. That is the suggested workflow for tracing. So we use the profile from before and call Scopy score on it, which tells us that the trace is to be 40 gigabytes in this case, and 6 gigabyte per MPI rank, which is the RAM requirement, which is needed during runtime per MPI rank. And when we look further down, we see that there's 1.6 billion calls, which are on average 0.16 microseconds long. So that's kind of bad. And by adding the -r flag to Scopy score, we can view these specific functions. And we will use these in a second to add them to a filter. So here we created the filter file, which we can then use with the -f flag for Scorpy score, just to update the estimate. And this time around, it's 400 megabyte and 70 megabyte per MPI rank, which is a lot better. And now we have two ways for filtering. The old or usual way is set the environment variable Scorpy filtering file to this filter file, and then execute the application like before, or recompile with the compile time filtering for GCC, and then repeat the step. And this will lead to a manageable trace file. All right, now I will hold a Vampyre demo. Are there any questions so far? Okay, so that is what you would see when you open Vampyre initially. This is a GROMEX run. It's a molecular dynamics of proteins, I believe. It has 4 MPI ranks with 4 threads each. The most prominent thing on the left side is the so-called master timeline, which has all the processing elements on the vertical axis, and on the horizontal axis it has time, and it shows coded in color which the currently active function is. In this case, you have a bit of a red for the MPI init and then a bunch of other colors. On the top left, you have all the different displays, which I will walk through in a minute. And this is kind of a thumbnail view. We call it zoom toolbar, which allows you to zoom more easily or gives you an overview where you are in the trace while zooming. I'll show the zoom in a second as well. Down here you have the legend, which tells you what is which color right now. And you can always change the colors by just clicking on these boxes and adjusting it. Okay, and this is the initial view of the context view, which gives you a few basic things about your trace run, the configuration, how you did it. Okay, that was the initial view. So the master timeline, as I said, currently active function over time. Think of the call stack is coming towards you, and you only see the top of the call stack on every pixel for each of these processing elements. The black bubbles indicate messages. This is a visualization chosen to reduce the amount of lines we draw. I'll show in a minute. This says that here there is messages being sent and received between these 3 partners, and the number of messages encoded in this bubble is 900. You can zoom into these, and eventually when the UI decides there's not too many lines to be displayed, it starts actually painting them. So here, for example, you have a number of send and receives and send receives. And these lines are the messages being sent. The other kinds of lines are collectives. These, for examples, are OpenMP forks. Or over here, there's probably an implicit barrier. Yeah, an implicit barrier. And as you can see, the thumbnail view shows you where in the trace you're located right now and how large the time is in which you're currently zoomed in. As you might have noticed, the display up here got updated. This display is the regular old profile, flat profile, and it gets updated over the interval which you choose. Let's go into the beginning, for example. So yeah, some initialization is taking place. what's there to see? I don't know. Just to show you that the zoom changes this display, which is a major thing. So you can, for example, zoom into one of your important iterations, and then you have the profile only for this iteration, which is a lot better than having all the initialization in the profile as well. All right. The next display I want to show you is the process timeline. It is the stack over time for one process, in this case, master thread 0. Same deal here, you can zoom in. And you notice that the timeline zooms in over all of them at once, which simplifies comparing things between processes or other displays I'm showing later. And those are messages again, the arrows, where you can see the details of the message down here. Due to the resolution, I can't really show it that well. You see interval, send number of bytes, which is a very weird number. Yeah, that display I already began to show was the profile, what we call summary. At the beginning, it might not be too interesting to see it for all functions. So what you can do is use the right-click settings menu that works in every display and is not context sensitive most of the time. And you can change it to show full groups. So now this time around, you can see that most of the time is spent in OpenMP loops, which is a collective term for fors, and I'm not sure which other kinds of loops. Lots of time is spent synchronizing in OpenMP. And then there's the rest. And some time is spent in FFTW, which is a fast Fourier transform library. There's tons of other settings you can do. For example, you can show fractions instead, or you can use a pie chart instead for shiny screenshots. Yeah, let me make that redo everything of that. Okay. In every display, you can use Control F, which allows you to search for things. For example, if I look for FFTW, I now have the list of functions here, and I press Enter, and it will jump to this one there. And if I do the same thing over here, I can highlight every occurrence of an FFTW call in the trace. That is helpful because the color coding you're seeing right now has to make a decision which pixel to color in which way. And a pixel in reality is a time range from begin to end of the pixel, and we have to decide how to color it. So one way or another, you don't see everything you might want. So you search for FFTW, and it says it's everywhere. And then you can zoom in, and it will show you the instances where the iterations are, where FFTW has been called. I think I switched to another trace now to demonstrate the rest. This is a CUDA trace, a fairly old one, from a particle in cell code on, I'm actually not sure where it's run. The first thing we can do is adjust the process bar height to fit chart height, which is nice if not everything fits onto your screen. And then we notice there's 4 processes with 3 or 4 threads each and a bunch of CUDA streams. And the first thing I want to show you is that you can filter in Vampyre. You can filter pretty much anything. You can filter out functions, make them invisible. You can filter out processes, make them invisible, or switch off parts of the visualization to help you basically find your way. What I'm about to do is just filter out all the other processes and their children, CUDA streams and threads, and just focus on one right now. Like that. And it updates the profile, it updates everything. So here you see one interesting feature is that you can see when the graphic card idles. And the other thing is that you can collapse CUDA streams on one card, which, because this is kind of a scattered view, it's not really helpful. So let's do that. Group processes. Processes is a collective term in this case. You have to kind of make a decision how to call threads, streams, and processes and everything. Group CUDA streams, boom. All of them in one bar. And we can do the same for the threads. And now they're all combined. And now let's zoom in once more. I want to show you one thing more. The message visualization I showed you is also used to encode GPU data transfers. So you can see a CUDA RMA put, which is in this case 0 bytes. Interesting. This one has 8 bytes. Yeah, so you can see when data is transferred to your graphics card, and you can see when it's idling, and you can also see what kinds of kernels are running. Yeah, the combined view is a bit different in the semantics of clicking. All right. That is what I wanted to show or showcase from CUDA. The next thing I wanted to show you is the scalability. This is a BlueGene P-trace made in Jülich from a weather simulation, and it's basically only tracing the load balancing layer, I believe. So let's fit to chart height once more, and we can see that the processes go down to 16,000. And what Vampyre does is semi-randomly picking processes to leave out. So it's not aliasing, it's more like leaving things out to display, because there are less pixels than there are processes to draw horizontal lines for. Another display which I haven't shown yet is the so-called communication matrix, which shows between all communication partners, MPI ranks, who talks to whom, and in this case, how many messages. You can also use, for example, the aggregated message volume, and then zoom in. Okay. Now I go back to our first trace. What I haven't talked about so far is performance counters, which is probably one of the most interesting things. We draw performance counters in this kind of way. So for this trace, I recorded the total instructions and the total cycles with the intent of getting the instructions per cycle later on. The visualization has two lines. One of them is the maximum per pixel, and one of them is the average per pixel. So this is the instructions issued per second in this case. And let's get the IPC. In order to do that, you right-click and you can retrieve the custom metrics menu, and this shows a bunch of custom metrics based on MPI and IO that already exist. We add a new one, call it IPC, and there's a nice visual editor. On right-click, you can add a new metric. And now we want instructions divided by cycles. Now we add an operation. It should be division. And this allows you to build the metric IPC for performance counters. Right. So what we see is that IPC ranges between 1 and 6. Now you can, if you have a function of interest, you can zoom in. By the way, this is for thread 0, same as the call stack over time. And you can, for example, investigate why there are peaks in the instructions per cycle. And in this case, you will discover that this is an MPI reduce, which has a very high IPC, and this is just busy waiting on a lock, basically. So IPC in this case wasn't very useful, but it's just to showcase what you can do. There's a different way of displaying counters, which is for all processes at the same time. Let me just adjust the bar height to fit the chart height again and close this one. So this time around, you display a counter for all processes over time, and you encode the value into the color. Let's pick IPC again. And it ranges from 0 to 6 as expected, and now you can see them all at once. There's also a way to overlay the above display with that. And again, you can zoom in to regions of interest, to iterations you want to see. I don't know. Then you can see, for example, how many IPC instructions per cycle FFTW does. You can adjust the color scale a little bit to leave out regions that are of less interest. And by making the scale more compact, you increase the visual difference for some parts, which can be helpful, which is definitely helpful for making screenshots. Okay, so that's performance counters. Now, the next thing I want to show is from a success story that we half a year ago presented on the OLCF website. It's a small tensor library which has 3 versions, one before it used the library, one after it used the library inefficiently, and then with the optimization. And the user used Vampyre to successfully improve its use, basically. And to show you that, there's a comparison view, which is one of the probably coolest features we have. So we want before, with slow, and with fast, in that order. And then you can load the traces, and it will load them all at once, and there they are. And in the background color, it's encoded which is which. I will close. I will leave the profiles open for a minute. So what I do now is I align these traces over each other by holding Control. And then I'll zoom in into the interesting part, which should be around here, maybe. I think it's there. Something like that. What's interesting is the border of the green part. So here it was like that. Here it got slower. Let me just, I think the CUDA things are invisible right now. Okay. And for some reason, this is on the wrong side. So yeah, the screen resolution makes it a little more harder to use this. And this is the culprit function, which makes things slower. So the code has been ported to GPU. No, was optimized for GPU, but the planning function, which decided on the kernel parameters, was actually occupying a lot of the CPU at the time. And the user used Vampyre basically to find out which function is in this gaps, which NVProf shows you the gaps. And it was pretty easy to find that out in the end. And the comparison view is a nice way to align two measurements exactly and show you the improvement, basically. Yeah, the comparison view. Anything else of interest? We have another user who likes to use Vampyre to just visualize his programs, not really just performance, but to gain a deeper understanding of what's going on in his code. So he custom colors every function he wants and looks at the interactions inside his code and makes slides like these. Yeah. And he likes that. All right, I think I'm done with the demo for now. Let's go back to the slides. Oh, are they still? Ah, okay. Demo over. So when you want to use Vampyre and Scalability, the first way you should go to the website probably. Once you've installed it or it's installed for you on a system, the -- help flags are always helpful. You can download the documentations from your installations or from the internet. ALCF has a website on how to use Vampyre and Scalability, including how to connect remotely to an HPC computer to use it. The support mailing list of Scalability is very good. And the last thing I want to say is that the VIHPS, Virtual Institute of High Productivity Systems, where I believe Paratools is part of, they do trainings and upload their materials. So one thing is you can probably invite them to do tutorials for you, 1 day, 2 day, or shorter. And they have lots of material online, which you can just use, like these slides, for example, but way more and more detail with a walkthrough, for example, how to trace BT of the NESPERL benchmarks. And with that, I want to conclude. Scalability and Vampyre provide a holistic, powerful performance analysis. Most notably, you can see everything in one picture. It's extremely customizable, extremely scalable, has many features, and is still adding more features for new technologies or what comes out of research. And it's been selected by OLCF over 7 years now to support their performance optimization efforts. So in comparison to other tools, Vampyre and Scalability they call it the high end of performance analysis. Future work, most notably user library wrapping, which is a very technical thing. It enables us to investigate library usage a lot better than before. And other than that, for example, we have an LLVM port, including a compiler plugin in the pipeline for the Summit systems and Sierra. We would be nothing without our sponsors. So that's the slide giving them some credit and the projects involved. And similarly, the people behind the projects. And yeah, with that, I want to conclude, and I'm open for questions now. Thank you.
Thanks, Ronny. Does anybody have any questions? No questions? You got one here.
Should I take the microphone?
Yeah, I think he's only going to be able to hear you.
No, you can just shout him out.
Oh, okay.
Okay, so my question would be that is, I'm getting confused about all the different performance tools. So what is the unique feature of Scalability and Vampyre that separates it from Tau and HPC Toolkit?
Oh, I have feedback. So HPC Toolkit is a pure profiler, I believe. So the timeline views you saw, you cannot get them. The Scorpy and Vampyre are a lot more detailed in that respect. Tau, I'm actually not quite sure about. I think they are kind of similar. I haven't seen the talk before. I think Tau is mostly a profiler as well. And in comparison to the vendor tools, for example, NVProf, we have the holistic view. You can view your MPI, OpenMP, and CUDA program in one big thing, which is a problem for these other tools. Sometimes you have to make a stripped down single node version, which just uses some of the features basically, which is not a problem with Scorpy.
So I'll just add a comment to what Ronnie said. There's a lot of overlap between the tools, but they sort of do have their distinct strengths and weaknesses. What I found personally is that Vampyre is probably the most scalable tracing tool that I've used. Understanding that profiling is sort of more lightweight, and HPC Toolkit and Tau excel at that. Tracing, you generate a much larger volume of data, and doing that in a scalable fashion, and then managing that data and visualizing it, it's a whole different problem. And so that's where I think Vampyre, I've noticed, is significantly more scalable than some of the other tools. So if you look at tracing for large, thousands of ranks or more, the Vampyre is particularly beneficial there. And I think they have a very good. One of the main differences, they collect a lot of the same data, the various tools. But the way they present it and the way you can look at it tends to vary across them. So depending on what you're looking for or what you'd like to look at, you may find one of the tools preferable to you than the others.
One more thing. The linear map or ARM map is also very similar. It has kind of a tracy view, but again, it's less detailed. But I would argue that a linear map is as scalable as Vampyre. It's just, it displays not as much to remain scalable, basically. Yeah.
Can I chime in about Tau real quick?
Sure.
Because Tau actually builds on top of Scorpy to generate OTF2 that's viewable in Vampyre. So the overlap there is that we completely overlap Scorpy. So if you're using Tau, you are basically using Scorpy at some level. So it has the same scalability, it has exactly the same visualizer, Vampyre. It's the same thing, but it also does profiling as well as tracing.
We can profile too. We also have sampling support now. You can all do it.
Yeah, I think it's certainly true that in the tools community they're fond of borrowing good ideas from each other. So
Definitely.
so you'll see any good idea that one tool develops often propagates across the spectrum of tools. One of the things you will find is that in the HPC context, certain centers, I think Oak Ridge, primarily their tool is Vampyre. So if you're computing out at Oak Ridge, you'll probably find that that's the best tool to use there, as it's the most supported. It's the one they're most familiar with, and they've worked out a lot of the kinks. At Argonne, Vampyre is kind of newer for us, but we've had good experience with it. Tau has been probably around the longest, and so at some centers you may find that they only provide one or two tools. You don't have your choice of all of them, and some on certain architectures may work better than others. Especially when you get into accelerators and novel architectures, some tools may have invested a little bit more in looking at that technology in advance of the other ones. So there's some distinguishing things there, but a lot of it is just personal preference too. If you like a tool, if you're familiar with it,
Definitely. So I personally use a linear map and Vampyre depending on how difficult the code is. You sometimes run across codes that are just very hard to get a grasp of, and then in the end, you just try to help the user, right?
Yeah, exactly. Are there any more questions for Ronnie?